Hey guys, tonight we're going to talk about the electromagnetic spectrum and all the waves that make it up. So to begin with, we need a really quick review of what we talked about in previous days. So keep in mind we mentioned that waves are oscillations that transport energy, and energy is the big thing here because we're going to be mentioning specifically how much energy each wave carries within the electromagnetic spectrum. Remember, we have two types of waves. We have mechanical, and those are waves that require a medium, and remember, a medium is something that you can travel through. Examples are sound, water, earthquake. Sound waves medium would be the air itself. Water wave would be water, of course, and then earthquake waves would be the ground that it travels through. Electromagnetic waves are the key to today's component. These are waves that do not require a medium. In other words, these guys can travel through complete and empty space, which is incredibly important to us when you think of things like wavelength and frequency. Because wavelength is the distance from crest to crest, or just one point of a wave to another similar point of the wave. So you could say trough to trough if you'd like, resting point to resting point, but it represents how long the wave is. And then frequency is the number of waves that pass a point in 1 second. Okay, so if we looked at something like this is something we went over in class earlier. Okay, you divided that line as a resting point, and you say that happened over a time period of 1 second. You could see one wave here, so that's wave 1. It's wave 2. And then you would count this right here as kind of a half a wave, because we just have a crest. So there I have 2.5 waves. I could say 2.5 waves over 1 second. So that's equal to 2.5 hertz, because that's the unit for frequency here. So number of waves per second, and then wavelength is the distance from here to here. Okay? Now, electromagnetic waves themselves, like we were saying earlier, travel without a medium. So they can travel through complete empty space. This is very important to us because we, on Earth, this is my sun, by the way, this is my sun emitting electromagnetic waves, can get energy from the sun. The sun is going to emit these electromagnetic waves which travel through complete empty space and eventually get to the Earth and begin to warm our atmosphere here. And from that we obtain energy. Incredibly important to us, and speed of electromagnetic waves are 300 million meters per second. Incredibly fast. Considering that the sun is 93 million miles away from the Earth, you can do a little bit of math and find out that it takes 8 minutes for a light wave to move from the sun to the Earth. And that's absolutely all due to the fact that they move at that constant rate. That's the speed of light right here. 300 million meters per second. Now, the electromagnetic spectrum is called a spectrum for a very particular reason, because it encompasses more than just one type of electromagnetic wave. We have many types. And tonight we're going to learn about all of those types. We have radio, microwave, infrared, visible light, ultraviolet, X-ray, and gamma rays. So take a quick look at this, and this is kind of going to summarize our entire lecture for the night. Just what do you notice about the wave as we move further right on our diagrams? If we start right here at radio waves, and we're moving this way as we go along, take a look at the wave. And what we see is that our wavelength begins to decrease. Because of that, so if we say wavelength decreases, remember lambda is our symbol, our frequency increases. And we notice our wavelength gets shorter here, it decreases, and all of a sudden we see a lot more energy. And that is going to essentially summarize almost everything we're going to talk about. So let's start on the far left of that spectrum with radio waves. They have the longest wavelengths of all of the EMS, or the electromagnetic spectrum, and the lowest frequency. So what you can equate from that is radio waves have the lowest energy of the entire spectrum. Now, just because they have low energy doesn't mean they're not useful to us, because You can see right here we use them in radios, TVs, radars, cell phones. So all of these kind of modern day components are available to us thankfully to radio waves. Radio waves are extremely long, anywhere from about 100 kilometers for a one wavelength to about 0.1 meters. So they've got a really big range, but they're very, very long wavelengths with low frequency. This allows them to travel pretty far and pretty well. One of the ways we use these is with radio stations. So what we can do is each radio is given their own radio frequency. They emit those radio waves, and then eventually they reach your antenna on your car, okay? And that antenna is going to take that radio wave and then convert it into a sound wave through your car speakers. Cell phones kind of do the same thing, hence the reason we need cell phone towers everywhere to emit and pick up these waves. And that way they're more useful to us. Same thing with TV. So all of these components are used thanks to radio waves, which remember have a long wavelength and a low frequency. The next one in our spectrum is microwaves. As we move up, all of a sudden our wavelength gets a little shorter and our frequency increases a bit, which means we have more energy. One of the most useful waves of a microwave is, of course, a microwave oven. And these ovens work by really one very simple premise. Within them they have a chip that is going to emit microwaves, hence the name microwave oven. These microwaves will be focused on whatever food you have in there. It could be this wonderful plate of pasta. And what these microwaves do is they cause the water molecules within your food to begin to kind of vibrate there. And if they vibrate, they're beginning to rub against one another. And we know that vibration and friction produces thermal energy, and because of that, your food begins to heat up. So microwaves, again, shorter wavelength, higher frequency, therefore slightly more energy than radio waves. Moving along the spectrum, we see infrared rays. Okay, prefix here would be infra, which means below. Okay, below red. We use these for thermography. You can see a picture of this thermogram right here. These are essentially night vision goggles that can pick up heat detection. We can see another picture here. Images like this, the eyes, or almost this entire image, that's the yellows and oranges, are producing more heat than the objects around them. And these can be useful with night vision, like we were saying, target acquisition, and all kinds of wireless communication. Moving along that spectrum is one of the most interesting ones is the visible light. Incredibly important to us because this is one of the only ones that we can see with the naked eye. So white light is actually a combination of all of the visible light spectrum, from red, orange, yellow, green, blue, indigo, and violet. Now, what makes these things different colors, and what it comes down to, is their wavelength. Okay? And the difference in wavelength is what's going to determine how we perceive that color. If you look over here, you'll notice the red wave in this picture has the longest wavelength, which means long wavelength, low frequency, low energy. When compared to the blue wave, you'll see that the blue wave has a smaller wavelength, which means a higher frequency, which means blue light technically contains more energy than red light does up here at the top of this spectrum. In the middle we find yellow and green, and we could find other various ones if we wanted to. So, quick recap of visible light. It's just a small part of the spectrum, but it's really important to us because it's the only part that we can see. Remember that red is going to be on the one end of the visible light spectrum. Blue or violet is on the other end of the spectrum. Red has the lowest energy of the visible light, and blue has the highest energy of the visible light spectrum. Look into ultraviolet now. So we're moving beyond the visible light, and we call it ultraviolet. Think beyond violet, because violet was the last one in our visible light spectrum, right? So UV all of a sudden begins, we see a lot more energy here. So more energy than visible light. And because of absorption in the atmosphere's ozone layer, more harmful types of UV light is blocked. We would love for it to all be blocked, because one of the hazards to UV light, okay, is skin cancer. And we tan and we also burn because of this UV light. UV light is so powerful that it can penetrate our skin cells and cause these skin cells to react in these particular ways, whether it be tanning, burning, or even possibly with too much exposure causing these cancerous cells. Now, UV light is, however, still very helpful because it causes your skin to produce vitamin D. So do we need the sunlight? 100% we need it. We need it in order to help produce vitamin D, which of course is good for our teeth and bones. But we don't need it in excess because, as we mentioned, this can cause skin cancer up here that we can call sun bleaching. So we do have some detrimental effects to UV light, but it is also still very helpful. Moving along the spectrum, more and more energy as we go, we look at X-rays. So waves are longer than gamma, but shorter than ultraviolet. Okay? In other words, they have more energy than ultraviolet, but they have less energy than the last one we'll talk about, which is gamma rays. Everybody's pretty familiar with what X-ray images look like. The reason they can produce these wonderful images is we have the X-ray machines, and what they do, I'm just going to draw a quick box right here. They essentially shoot particles, these gamma rays, hence the reason, X-rays, and they'll shoot it at, let's say, whatever object you have. I'm just going to draw a random shape, and then they put an X-ray film behind it. Now, some of these X-rays may be absorbed by this object, and then ones may go through, and what this does is eventually produces a picture for us. Thankfully, due to the different densities of things like bone and teeth, they'll absorb the X-rays, and that's what produces these white spots in these images, especially where teeth and bone are supposed to go. Once again, because they're so powerful, too much exposure to these can cause cancer. Hence the reason when someone's giving you an X-ray, they leave. If we look at the last one, we have gamma rays. These are the highest of our energies when we look at the EMS spectrum. They're the smallest wavelength, they have the highest frequency, and they're incredibly energetic. They're incredibly dangerous to us. These are what we were talking about in radioactive emissions earlier. So we see these naturally with radioisotopes. We can see these produced in nuclear explosions or nuclear power plants. And they cause some serious damage when absorbed by living cells. They can actually make cells convert into carcinogen cells. They can also kill cells. So gamma rays, incredibly powerful. We're just on the brink of really being able to harness their energy and use them for technology. But just most importantly, they're the shortest wavelength, highest energy, and at the end of our electromagnetic spectrum. Here's a pretty quick summary of everything, ranging from radio here to gamma ray at the end. If you can just kind of remember that we start with a really long wavelength on here, and then we have a shorter wavelength at this end, low frequency down here, high frequency here, low energy, high energy. Essentially, if you're able to answer these 5 questions right here, I think you're well on your way to understanding, and tomorrow in class we'll begin discussing these in much more detail. Have a good one.